okay, which are along the, not along the equator but along the equatorial plane, okay, which basically means that we are fixing trajectories which is of the form theta equal to pi by 2. So with this condition, theta remains constant of course, so the theta equation is not relevant anymore. But we have three other equations that we have to solve. So first the T equation. Then the rho equation. Okay. So our goal will be to try to solve these equations to find the general trajectory. So let's start with the phi equation. This can be easily solved because what you can do is that you just multiply the phi equation by d phi du inverse. So d phi du inverse d phi plus 2 over rho 0 du is equal to 0. Well, I should remind you that prime means del rho, rho derivative. So this gives ddu of log d phi du plus log rho square 2 log rho equal to 0. Is this okay? So this can be easily integrated. So this is constant. This is constant. And now we can exponentiate it to get rho square d phi du equal to k, where k is some constant.
So how you can connect your d phi du?
No, it could be plus minus k. So whatever it is, I call it k.
But you have taken log of d phi du.
Otherwise, you can take mod of log of mod d phi du. Okay, so mod d phi du will be k over rho square, in which case k will be positive.
Sir, I can always simplify parameters in such a way as to make
Phi is increasing, yes, that's also fine. Right, you just change u to minus u and then d phi du will be positive.
But it will be always a monotone.
It doesn't matter. I mean, in some region it's positive. Right? So in that region you evaluate it and you get this equal to constant. Right? And then you just follow it from there. Right? If it changes sign, it will automatically come with that. You should see somehow that this is changing. But in this case, you know that it's because we are getting this equal to constant. Right? It cannot change sign, right? Because it's constant. As long as this constant is non-zero, right? This can never become zero. So in d phi du, if you start with positive, it will always remain positive. right? And this you can recognize as a consequence of angular momentum conservation. Right? This is what you normally get in central force problem as angular momentum along the z direction. Is this okay? It's not quite the angular momentum yet, because this is ddu, whereas normal the angular momentum is called ddt. Okay, but you will see that it can be converted to angular momentum.
Define the tau. So I have to define.
Okay, it depends on what you. If you go try to make connection with the standard angular momentum, then this is d phi dt. Right? So something is concept, right? This is concept in terms of u, right? And u and tau are related by simple multiplication. So rho square d phi d tau will also be constant, right? Because tau is proportional to u. Rho square d phi dt, as we will see, is not constant, but some combination of rho square d phi dt and something else will be constant.
So there d phi d tau can be constant?
Yes, because u and tau are just proportional to each other. Then u is affine parameter, and tau is a possible choice of affine parameter that we have seen.
So in that case, rho square d phi d tau, that is the angular momentum?
That is also constant. Well, it depends on what. I mean, as I said, if you want to make connection with the standard angular momentum, right? It's rho square d phi dt. Right? Now that is not constant here. Okay, but you can convert this to rho square d phi dt times something. Okay, so that you can call angular momentum, or equivalently this is angular momentum, right? If you want to define angular momentum as something that is conserved, right, which is what you will get from Noether charge, then it's this one, which you replace by tau. Okay, u and tau are just related by an overall constant, normalization constant, right? Or if you want to write in terms of t, okay, then you will see that it's not rho square d phi dt, but it's multiplied by something. But this constant that we have is clearly related to the angular momentum, which will be at most related by multiplicative factor. Okay, because u and tau need not be the same, right? U and tau can be scalar.
Phi dt, in case of d phi dt, something will be multiplied. That can be visualized from here, that we can change it to be d phi dt times dt du, which we can solve from the other equation of t.
Yes, but one has to change that whether that what that object is.
Yes.
Right? That is solved from the other equation. Okay, so let's now look at the t equation. Okay, that also looks simple. So this is the last equation that we'll try to solve. So t equation is also not hard to solve. All you have to do is to multiply this by dt du inverse. So dt du inverse times d2t d square plus psi prime over psi 0 du equal to 0. So this tells us that ddu of log ddu plus log psi equal to 0. Okay, because now you have to remember that psi prime is d psi d rho. So psi prime times 0 du is actually d psi d rho. Okay, that's why it becomes ddu of log psi. Okay, so ddu is not the same as prime. Okay, you have to multiply by d rho du to convert psi prime to ddu of psi. Is this okay? So this tells us that this is constant. And hence dt du times psi is equal to some other constant here. This constant. Okay. So now we will use the fact that Q is an affine parameter, but it's defined only up to a multiplicative factor. You can always multiply U by any constant and still have it as affine parameter, right? Your equations are unchanged. So because this is a constant, we can now scale U appropriately to set this constant equal to 1. Okay. So setting this equal to 1 just fixes the normalization of U. Okay. So use the freedom of scaling U to set n equal to 1.
That is a choice we are doing, but we could have done the same thing on this side, right?
On which side?
This rho square d phi du equal to k.
Yeah.
We could have made this to be 1 and kept that to be
then that constant would be something physical. Yeah, exactly. So by scaling U, you can set one of the constants to 1, but not both. Okay, and it's basically the ratio of K over L, which is a physical quantity. Right? That you cannot change by scaling U. Okay, so let's write that equation. So we'll write u psi d p du equal to 1. Okay, so these are the equations you have.
Now we can show that this d phi dt rho square d phi dt times psi is a constant.
Yeah, you have to multiply by 1 over psi dt du, right? Multiplying that remain.
Now du is not tau.
Du is not?
Tau.
We don't know. Right? We will see how the relationship between u and tau is. Okay, right now we have already fixed the normalization of u, so we cannot anymore demand that u is equal to tau.
Yes.
Right? You can relate it to tau by some constant multiplication. Okay, so now we are left with this equation, right? So the first thing we do is to simplify this using whatever we have done, because d phi du and d psi du, dt du, we have already calculated, so you can substitute for this. So d2 rho du square plus phi prime of 2 pi 0 d square minus rho over pi. So d phi du is whole square is k square over rho to the 4. And then plus psi prime of 2 pi, and dt du whole square is 1 over psi square. Okay, and now I can also use psi times chi equal to 1 to get rid of this factor. Right? Psi and chi are just inverses of each other.
So psi and chi equals to 1, that requires scaling t.
That requires?
Scaling t and not u. Psi making psi.
Yes,
times
exactly.
psi equals to
Yeah, because u is a property of the geodesic, right? It's not a coordinate of space-time. So we are not doing anything to the space-time coordinates anymore. Is this okay? So even though I'll proceed with psi chi equal to 1 for, I mean it's instructive often to keep psi and chi independent and carry out this calculation, okay? Because we will see the final result that we get will depend both on psi and chi. Okay, typically the result that we will get will depend both on psi and chi, okay? And that's important because so far the kind of effects that I have discussed for gravity involves only G00, right? The gravitational redshift, for example, okay, the slowing down of the clock that we discussed, that relied on G00, right? G00 is the one that we identified as with the gravitational potential, right? So far the Gij part hasn't really played any role, okay? But chi is something that appears as coefficient of gi, right? The space. So even though so far chi hasn't played any role, right? Everything that you could do, okay, is only sensitive to psi. Okay. When you try to do a detailed analysis of the orbits, right, then both psi and chi are important. Okay, so if you want to see separately the effect of psi and chi, you can keep psi and chi independent in this analysis, and at the end you can see the effect of psi and chi independently separately. Okay, but I will proceed by setting psi chi. Okay, so I want to integrate this, and the way I will do it is to multiply this by d rho 2 chi, so multiply by 2 chi times d rho du times this.
So chi prime by chi can be written as minus chi prime.
Yes, it can be. So I will write everything in terms of chi.
Okay.
But doesn't matter. Okay, I can write also everything in terms of psi. I can write everything in terms of chi and then replace chi by 1 over psi also. Okay, so 2 chi d rho du we multiply by. So we get 2 chi d rho du times d2 rho du square plus I prime d rho du times d rho du whole square. I could have written it as cube, but I am for there's a reason why I am writing it as a product like this. 2 chi pardon? No, 2 chi I have multiplied by. So 2 chi d rho du. So 2 chi d rho du come here. So 2 chi goes away from here.
We are writing this d rho du separately so that we can write del chi
Yeah.
del u.
This can I want to write as d du of chi.
Yes.
Okay? Because that's what we saw, that we need the d rho du to convert the primes to u derivative. Okay, so this one is minus 2 rho 2 k square over rho cube times d rho du plus psi prime over psi square. Okay, I don't even need to set psi equal to 1, psi prime over psi square times d rho du. So now I want to write it as d du or of something. So this I claim is d du
Chi
Of
rho du square.
chi d rho du whole square. Okay, because this will give you two terms. One is chi times d du of this, which is going to produce this term. The other one will be d chi du times d rho du whole square. So that's this term. Okay, this is d chi du.
Plus k square over rho square.
So you get a plus k square over rho square plus minus 1 over psi.
Minus
Plus or minus?
Here? Oh, because when you take the derivative, you get a minus sign, right? Is this okay? Right? So this whole thing, so this also I managed to integrate. Okay. Now the fact that one is able to integrate these equations, right? Because we had a set of second order differential equation, right? The reason that we are being able to integrate this is because there are some conservation laws which allows you to integrate. Okay? I mean, if you start with the Euler procedure and start developing the conservation laws, then you recognize why you are able to integrate it. Okay? But right now we are just proceeding in the naive way, okay? Just taking the equations of motion and manipulating this to try to integrate them. Okay? But this is the reason that we are being able to integrate this is because there are enough number of conservation laws hidden in this problem.
So
There is basically angular momentum and the inertia.
yes, sir.
Okay? That we know is enough to integrate a three-dimensional problem. Okay, and that's what we are using here. Okay, except that we have not done it that way. Okay, we have not first derived the conservation laws and then tried to get this, but that's the reason why we can integrate this in the first place.
So we have gotten two conserved quantities.
Yes, the other one we have not written, that's the L square. See, if you remember the central force problem, the mutually commuting conserved charges are Lz, L square and energy. Right? So, see this, according to we have it looks like 2, but it's not actually 2 because you have to eliminate T, right? Or eliminate U, right? Because the usual we think of conservation laws, right? We think of the 3 space coordinates as a function of T. Right? So you can go to that language, right? So for that you have to eliminate U. So this is one conservation law. Right? This is the second one. Okay, this you can also convert in terms of T derivative.
So there are three
The
concepts.
third one, the third one is not visible. This is not really a conservation law. Okay?
Oh.
This you can think of as something that allows you to convert T derivative to U derivative, or U derivative to T derivative, right? Because when you think of conservation laws, right, in a classical problem, it's 3 coordinates which are functions of time, right? So it's a problem with 3 coordinates and 3 momenta, right? And you know that in order to integrate this problem, we need 3 conserved charges which are mutually commuting, right? And in the central force problem, we know that the way we solve this is that Lz, L square and Hamiltonian, these are the 3 conserved charges which have vanishing Poisson bracket with each other, right? So the same thing is true here, okay? Because you have time translation symmetry, there is an analog of Hamiltonian which is conserved, okay? And because you have full rotational symmetry, Lx, Ly and Lz are all conserved, but they don't have vanishing Poisson bracket. Okay, so Lz and L square, they have vanishing Poisson bracket with each other. So you can use Lz, L square and H, okay, as a 3 conserved charges to integrate the system. Okay. So if we didn't do anything and just started from those conserved charges, we could systematically proceed and integrate, okay, exactly as we have done in classical mechanics.
So other conserved charge means at the beginning we have said that d theta du equals to 0 to 0.
Yeah, so that information has gone in there.
Yeah.
Right?
That is another concept.
Exactly. Okay, as a vector, L is conserved. Because otherwise, if you rotate the axis, right, Lx and Ly will not be conserved. So that information has gone in there.
So can we think can you think that theta is equal to constant is another
That's the
kind of
What is constant?
theta equal to constant is a solution of the problem.
Yeah, but theta by itself is not a conserved charge, because if you start with another orbit, which is not theta equal to pi by 2, then theta is not conserved. Right? So in that sense, theta is not conserved. It so happens that theta equal to pi by 2 is an orbit because of the conservation law of the full angular point.
The fact that at some coordinate system I get theta equals to constant is
Is a consequence of the conservation of Lx and Ly. Right, in this case, because you start with an orbit which is theta, where theta equal to pi by 2 and d theta du equal to 0, right, to begin with. Then the reason that you cannot generate non-trivial d theta du is because that will change Lx and Ly. Right? Whereas the initial condition is such that only Lz is non-zero, Lx and Ly are 0. Okay, so let me now write down the third relation. So that will be phi d rho square plus a square or a square psi equal to n. Okay, n is another constant quantity. Pardon? Well, it's not quite a Hamiltonian because it's U derivative, right? You have to convert it to T derivative to get something. Yeah, so, but that you can always do, right? So in fact, we will now eliminate U altogether, okay, and write everything in terms of phi and T and rho. So let's do that. So eliminate u. So eliminate u. U using ddu. To 1 over psi. Okay. So anytime you have u derivative, I can write it as 0 dt times dt du. Then I'll replace dt du by 1 over psi. So chi over psi square 0 dt square plus a square rho square minus 1 over psi n, and this becomes rho square phi dt times 1 over psi and as I said, chi can be replaced by 1 over psi. Okay, because from what phi and psi are related. Okay, so let's now try to calculate, try to find an interpretation of n. So n is given by this. Okay, maybe I'll come back to that a little later. Okay, so let's try to calculate d tau square. Okay, because we have already fixed u, right? There is no further freedom in scaling u. Okay, so in general tau and u are not equal. Okay, but so let's try to see what d tau square is along the path. So d tau square is minus ds square. So that will be given by psi times minus psi dt square plus chi dr square plus rho square theta is constant, d rho square. I am sorry, this should have been, because we are using rho as a radial variable. Okay. So this I can write as psi. So d tau du whole square. So you are trying to find a relationship between tau and u. D tau du whole square is psi times dt du whole square. Okay, dt du is from here 1 over psi. Psi times 1 over psi square. Minus chi times d rho du whole square. Chi d rho du whole square is given by n minus all this, right? So n, not even chi, right? Chi has gone, because chi d rho du whole square is directly this, so minus n minus a square over rho square plus 1 minus 1 plus 1 over psi.
So which step?
And minus rho square d phi du whole square, so minus rho square times d phi du whole square is k square over rho to d 4.
Bracket should be not.
Pardon?
Bracket should not be there.
These brackets should not be there. Let's say minus chi d rho square. So minus chi d rho du whole square
Minus n and plus k square.
Something is not quite correct.
No sir.
It is okay?
It's okay.
Because it will be minus, there it will be minus chi.
It is minus chi d rho du.
Minus chi d rho du square. So that will
Yes.
be
Chi d rho
minus n
du.
plus k square rho square minus 1.
Yes.
Yeah. Okay. Okay. So now you can see that there are several things cancelled because 1 over psi cancels against this 1 over psi. K square over rho square cancels against this k square over rho square. So this is just minus n. Okay, so n basically fixes the relationship between tau and e. Okay. And it's also now clear that the trajectory is characterized by these two constants k and n, which is what we expect because we expect for a classical particle moving in a central potential the trajectory will be controlled by the energy and angular momentum. Okay. Once you give the energy and magnitude of the angular momentum, then the trajectory should be given. Okay. So this you can think of as the two constants that represent energy and angular momentum.
So for time like this, n should be
Yes. So now you see
negative.
that if we have a physical particle moving, massive particle, then n should be negative, right? Because d tau square is positive for massive particle. So for massive particle, we must have n less than 0. For massless particle, we have n equal to 0. So far we have not distinguished between whether they are talking about massive or massless particle. But now we know how to distinguish between them. That if we are studying the motion of a massless particle, we have to set n equal to 0. If we are studying the motion of a massive particle, we set n equal to some negative constant. Okay. So here we have these two equations. But something is wrong. N should have been positive.
Where I define
Well, we'll see. Because physical particle has non-trivial, non-vanishing. Oh, maybe because of this minus 1 over psi. Because psi goes to 1, right? As in the asymptotic. Anyway, when we study massive particle, we'll see what it is.
So can you
Pardon?
what
No.
is
I haven't said anything. Forget about what I said. We'll study it later, right? But you just see from here that n should be negative for massive particle, right? I was just worried that, I mean, for a physical particle these are positive, so how can n become negative? But the point is minus 1 over psi, right, is negative, and that's not going to 0 as rho goes to infinity, right? That actually goes to 1. Okay. So now there is one more step, and then we will specialize to massive and massless particles. So this step involves finding the trajectory. You see, at this stage, these tell us how rho and phi evolve as a function of time.
So in principle, I can find out.
But suppose you are not interested in how it evolves as a function of time, but you are only interested in knowing the trajectory. Okay?
So we can
That means
eliminate t.
we have to find rho as a function of phi. Okay, so that's easy. It's the same principle that we, just like we eliminated u, right? We have to basically use one of these to convert d rho dt into d rho d phi, right? We can use this equation to convert this into d rho d phi. So d rho dt I can write as d rho d phi times d phi dt, and d phi dt I will substitute k psi over rho square. So for the trajectory, I will get chi over psi square d rho d phi square times d phi dt, which is k square psi square over rho to the 4 plus k square over rho square minus 1 for psi. Okay, this of course doesn't mean that this is not important. So we may actually want to know how much time it takes for phi to change by a certain amount, right? So for that we have to use this equation. Okay. But if you only want to know how the particle is going to move, then this is enough. So some things of course simplify. Psi square cancels. Okay, so now we specialize to massless particle first. What is it that you want to calculate? Let's imagine that we have this point at r equal to 0. Or rho equal to 0. Okay, that's where the center of the black hole is, or center of the massive object is. And we want to consider a ray of light coming from far, bending and going like this. And it's clear that far away from the center, these will be just straight lines. Okay, I am thinking in terms of Cartesian coordinates. Okay, far away. Because far away, of course, the metric is Minkowski, so the Cartesian coordinate system is a useful thing to use. So, what you want to calculate is this angle. That initially if it was travelling along some certain direction, how much its trajectory gets bent, by what angle its trajectory gets bent. Okay, that will be our object of interest.
So this bending that takes is greater than whichever it is the physical radius or
Pardon?
this from point to the curving line, this distance should be more than the
Yes,
first
certainly.
radius or
Yeah. So this distance rho 0 is outside the physical radius and of course outside the Schwarzschild radius.
Yeah.
Okay. So it's large. Okay. And I mean it's a good approximation to take this to be large compared to Schwarzschild radius, because if you take for example an object like the sun, okay, the Schwarzschild radius of the sun is of the order of 3 kilometers, while the physical radius of the sun is something like 700,000 kilometers. Okay. So this ratio is extremely small, right? So this rho 0 even if the light grazes the surface of the sun, it's still far away outside the short cell radius, right? So that's an approximation only using. So basically what we are saying is that this 2gm over rho naught, this factor, this is the short cell radius, this rho naught is the distance of closest approach. Okay, that's the minimum value of that is the physical radius of the object, right? If you enter the object, then of course you cannot even use the matrix that you have used. So this typically we can take to be very small. In particular for sun this is 3 km, this is minimum value of this is 700,000 kilometers. Okay, so clearly this ratio is very small. So you will be making that approximation but not immediately. Okay. So in that approximation the effect of gravity is weak clearly, and you expect that this bending will be small, right? That this distance, the angle between these tangents will be small. Is this okay? Okay. Now we have to convert this problem in terms of the variables that we have here. Okay, what does this angle correspond to? What kind of change is involved in computing this angle? So for that we will be using the following geometric relation, that we know that far away from the object, okay, much farther than rho 0 for example, asymptotic, this becomes a straight line. Okay, this also becomes a straight line. So let's imagine that we have a straight line. And now suppose we draw, suppose here is the object, we draw a straight line from the origin to this object. Okay? So it's clear that the farther and farther you go, this angle becomes smaller and smaller, right? In the asymptotic limit, this angle goes to 0. And the same thing happens for the object which is going away, far away. Here, this angle is going to 0. So if you want to calculate the angle between these two tangents, two straight lines, okay, which are far away, okay, and there of course the notion of angle is the usual notion as we have in Cartesian coordinate system, right? Because this is just a standard for straight line far away from the object. So this angle, the angle between these two tangents, then this angle is the same as this angle, because this line is parallel to this and this line is parallel to this, right, far away. So this is a change in the azimuthal angle, right, because this is moving along in the equatorial plane. So this is nothing but what? How much phi changes. So this delta phi is integral from minus infinity to infinity d phi dt times dt. Is this point clear? But you are not interested in delta phi. What you are interested in is that how much the deflection is, right? Small delta phi. So this is capital delta phi minus phi. And even if there is no gravitating object, okay, moves along a straight line, okay, even then the azimuthal angle that we will see from here will change by pi, right? A straight line coming from that end going this way, right? You are measuring the azimuthal angle. So the azimuthal angle changes by pi. Okay. So even without any source of gravity, the azimuthal angle would have changed by pi, right? That's not what you want to calculate. So what you want to calculate is the extra deflection, and that's given by the total change in the azimuthal angle minus pi. Okay, so this is what you need to calculate.
So, yes. E taking from minus infinity to infinity.
Yes.
How does that imply that it's coming from here far and going here far?
How much? Well, you can also take rho. I mean, you can also write it as d phi d rho times 0, right? Rho comes from infinity to rho naught and goes far. But in the frame of the in any fixed time frame, right? Even if it's a photon, right? Its proper time is 0, but it will come from a minus infinity and go to plus infinity, right? Okay, so because d phi dt is finite in measured from a stationary observer, right? Is that the photon's proper time is 0. Right? Doesn't mean that the photon travels from one place to another instantaneously, right? In our time, if we are measuring, it takes a finite time. Right? So in our frame, we will see that it's coming from minus infinity and getting deflected to plus infinity. Is this clear? Okay, so once it's clear what you have to calculate, then of course the calculation is straightforward, right? Because you have all got all the equations anyway. Okay. But what you need to calculate is the change in the azimuthal angle, right? Because this change in the azimuthal angle is what gives us the angle between these two asymptotic trajectories. Okay, so I only need this equation, so let's erase that. So n is 0, right? For photon, so you have n equal to 0. N equal to 0. So d rho d phi is given by rho to the 4 rho square over a root pi. More d rho d phi. So you are taking the square. Yeah, it is a minus because I have to take this to the other side, right? Minus. Because what I did was I want to solve for d rho d phi, so I took this out on the other side, setting n equal to 0. So 1 over psi minus k square over rho square. This is the square root of the whole thing.
And we take only the positive value.
What will take only positive values?
So mod.
No, because this was square. Square was given by this, right? So I took the square root. So d rho to d phi could be either positive or negative. That's why I took more. Okay? Because this is positive by construction. Okay, I've taken k to be positive. Otherwise, I have to write mod k.
So if k is some exponential times some number that we have seen. Because log
Yes.
of everything was constant.
Yes.
So taking anti-log, that means the exponential something cannot be negative. If k is here.
Yeah, but the point is, there is a mod involved there only, right? Because it's like if you have dx 1 over x dx dt, right? When you integrate, you get log of x equal to something. So x is always exponential of something, right? But that doesn't mean that x is prevented from a negative, because while integrating itself, you should have written a mod. So x could have been negative, Right? That's why the question was d phi du is positive or negative. Right? There I could always choose u so that d phi du is positive. But that's not the case for d rho d phi. Okay, in fact we can see from this diagram that phi goes monotonically, right? But rho is not like that. Rho is a radial distance. Okay, rho reaches a minimum value and then goes up.
D rho do phi really changes.
Yeah. So d rho d phi really changes sign, and it changes sign exactly at rho 0. Right? This is the closest approach. Okay. So this also allows us to fix the relationship between k and rho 0. Rho 0 is something physical. This is the closest distance, right? K we have not interpreted yet. Okay, although we said something like angular momentum, but now we can fix the relation because we know that at rho equal to rho naught, d rho d phi should be 0. So this tells us that k square over rho naught square is equal to 1 over psi rho naught, or if you will take k square, k is rho naught over psi rho naught. Okay? Because this has to vanish. Okay? If d rho d phi has to vanish, okay? These are of course k is constant, none of these are going to vanish. Okay? So this has to vanish, and that tells us that k and rho naught are related by this. So this means that you can forget about angular momentum if you know the closest approach. Okay, if the light is bending and if you know the closest distance that the light approaches to, okay, then that you can use to calculate your k. Okay, now it's also clear from this, from the symmetry of the problem, that the change in phi from minus infinity, from this asymptotic up to rho naught, will be the same as from rho naught to infinity, right? Because this trajectory is symmetric around this point. So you can just calculate the change from rho naught to infinity and multiply by 2 to calculate the capital delta. So capital delta phi, and the reason we are doing this is just so that we don't have to take into account these different signs here, right? Because d rho d phi is positive in one, negative in the other. Okay? But d rho is changing, d rho is changing sign, right? Not d phi. Okay, so for d phi, it's just adding the total derivation. So delta phi, then we can write as 2 integral rho naught to infinity d phi d rho times d rho. And in this part, rho is increasing, phi is increasing, so d rho d phi is positive. Okay, so you can use plus sign there. Okay, there is no more, this confusion of mod etc. are not here. So this is 2 integral rho naught to infinity d phi d rho. So k root chi of rho over rho square times 1 over delta minus k square over rho square plus 1 psi. And you can now also write it more explicitly as 2 k is rho 0 over square root psi of rho 0 okay, I am using the fact that chi of rho is 1 over psi of rho. Okay. And now that 1 over psi of rho, okay, 1 over root psi of rho I am going to take inside. Okay. So minus psi of rho over rho square. For k square I will substitute for rho 0 square over psi of rho. Psi of rho 0 plus 1. Instead I have just done several steps at one go, so let me say it again. So k I have taken out, rho 0 over square root of psi 0, psi rho 0, right? That is clear. So here I wrote chi as 1 over psi, okay, rho square is as it is, chi as 1 over root psi, okay, and then I took the psi inside the square root. So then we got minus psi of rho over rho square, and k square I wrote it as rho 0 square over psi of rho 0. Just explicitly substitute for k square. The second term, psi of rho has gone inside, so psi of rho times 1 over psi of rho gives you 1. Is this okay? Okay. So now that once you have got this, okay, we know the expression for psi of rho. So you can just ask the computer to evaluate it, right? It's completely well-defined expression, so you can evaluate it on the computer. But you can see, try to get an approximate expression to what kind of deflection you expect. Okay. So for that you will make this approximation that is written here. 2 gm over rho naught is small.
So rho 0 is the distance to closest approach.
Yes.
This is not
This is not?
Schwarzschild radius.
No, this is not Schwarzschild radius. So this is Schwarzschild radius.
Yeah,
2 gm, right? And you are using the approximation that this is small, right? That you don't go anywhere close to Schwarzschild radius. And this is true for physical objects, physical stars, right? The sun, for example, where this bending of light was first measured. Okay? Its Schwarzschild radius is much smaller than its physical radius. Right? So if you are studying the bending of light around the sun, right, you cannot approach closer than the physical radius. Right? So that's this rho 0. Okay, that's like 700,000 kilometers, whereas this is like 3 kilometers. Right? So you are forced to have small 2 gm over rho 0 anyway. Okay, so what you want to do is to evaluate this in that approximation. Evaluate it in that approximation and see what we get. Now, it's straightforward except that we have to be a little careful because the denominator here vanishes at rho equal to rho 0. Yeah, the integration is starting from rho 0, so the denominator vanishes. That doesn't mean that the integral is ill-defined, okay, because this is integrable singularity. This is like integral dx over root x. Right? Dx over root x is certainly integrable, right? When you integrate, you can just get half root x or 2 root x, right? That certainly is not a problem at x equal to 0. But nevertheless, we have to be a little careful before we expand it out in parts of this.
This will be some finite result because the form of the function if rho.
Yes, exactly. It will be some finite result. But what I am saying is that we want to expand this thing, psi of rho, for example, in this approximation. Right? So while carrying out that expansion, right, if you do it in the wrong way, you will start getting more and more parts of this, the leading term, 1 minus rho 0 square over rho square, right? You don't want to get more and more parts of this in the denominator. Right? Then successive terms will start diverging. So you have to be a little careful before you expand. Right? So the idea is you will first extract out the divergent piece, right, in the integral and then expand the rest of the terms. Okay? And the divergent piece will be a square root. So let's go through it in a little more detail anyway, okay, because the approximation methods are useful to keep in mind. So this I can write as 2 rho 0 over square root of psi of rho 0 So now I am going to let's do one thing. Let's just do one more step. So I'll write it as minus psi rho over rho square plus psi rho naught over rho naught square minus half, and cancel out this term. Okay, so what does it mean? This means that in the denominator we have 1 over square root of psi rho naught over rho naught, right?
Put it that in, right?
We can put it in the inside. Okay? So that means inside it becomes square of that. So we have a psi rho naught over rho naught square. We are multiplying by it. Right? So psi rho naught over rho naught square cancels out this term. So minus psi over rho square is the first term, and then psi rho naught over rho naught square is the second term. Okay. So now let's write down explicitly the expression for psi 0 over rho square times minus 1 over rho square plus 2gm over rho cube plus 1 over rho naught square minus 2gm over rho cube equal minus. Okay. Change variable u equal to 1 over rho. So u naught is 1 over rho naught. So this becomes equal to 2 integral u naught to 0 to u naught. Okay, you see that this du becomes minus 0 over rho square. So that's a minus sign, but that corresponds to changing the integration limits. Okay, it becomes from 0 to u naught.
So it will be rho naught cube, so in the last row.
Rho naught. Rho naught. So this becomes du times u naught square minus u square plus 2gm times u cube minus u naught cube. This I can write, but let's do one more simplification. I define V as U over U naught. Okay? So du naught dv. So this becomes down now from 2 integral 0 to 1 dv. The U naught that comes from the scale change actually cancels the U naught that comes from inside. Okay? So dv 1 minus b square plus 2gm u naught times b cube minus 1. Is this okay? Okay, I am just changing variable from u to v by scaling to u naught, right? So u is u naught v. So if you do that, so this du becomes u naught dv. Here you get u naught square minus u naught square v square, and here u naught cube v cube minus u naught cube. Okay, so a factor of u naught you can take out, Okay, and that because it's minus half, okay, that cancels the u0 that comes here. Okay, that's why you got this expression over here. And now it's clear that the whole thing depends only on this ratio, 2 gm over rho naught. Right? Otherwise, it's just a numerical number. It's also clear, I think, that now we can expand. Okay? Because now you see that 1 minus v to the minus 1. This is the one that is singular near v equal to 1. This has been taken out as a factor. Right? This is perfectly non-singular. So this one can be expanded. So this gives you 2. So this is the first time I am making an approximation. Right? So far there is no approximation. This is just a manipulation of the original integral. Right? So you could just manipulate the original integral. If you really want to calculate what happens when the light goes close to the black hole. Right? Imagine that you have a genuine black hole, right, for which the actual radius is smaller than the short side radius. Then you could imagine throwing a light that raises the object, okay, the horizon. Even then this formula is valid. Okay, is that this number is no longer small. So the next step that I am going to do is not valid anymore. Okay, but till then this is valid. So the next step will be to expand it. So 1 plus v equal half, and then you get 1 plus 2 gm over rho naught, 1 plus v, 1 plus v, that is v square. 2 is not there because it is minus half, plus higher order characteristics. Okay, those are higher powers of gm over rho naught.
Half or minus half?
Pardon?
1 plus v to the minus half.
Because there is a minus sign here. Oh, here, minus half. So the first integral is elementary. Okay? This you are probably all familiar with, right? 1 minus v square to the minus half. Okay? This gives you pi by 2. So 2 times pi by 2, that's the pi, right? Which we expect. So you are calculating the capital delta phi, right? Yeah. You have to multiply, subtract pi from there to get the small delta phi. The second part, second integral, is not elementary, but it's still doable. I'll leave it to you to try to do this, or you can put it in a mathematical and ask it to do it. Right? You will get the answer in a second. Okay? This second integral. So that gives you 2 times, let me write, this is 2 times pi by 2 plus 2 gm over rho naught. So that's pi plus 4 gm. So this is our delta phi. Is this okay? So this, in fact, was one of the key tests of general relativity. Okay, the bending of light. And the way it was performed, you probably have all heard about it, right? Because if you, I mean, normally we see stars, right? And we know exactly at which angle the stars are. Okay? But to bend it, some object has to come in front. Right? Because then the light will bend, and then apparently it looks like the star is at a different angle, right? You see, suppose the star light, suppose you are here, and the star is here, we see the light from the star. Now imagine that in the same configuration, some massive object has come in front, okay, like the sun. Then what is going to happen is that the light is going to deflect. Okay, we are still big enough to catch the light, so the light is going to deflect. And reach us at an angle, so we like to think that light is coming from a different angle. Right? This is what's called a parallax, right? I mean, originally we thought the star is along one direction. Now, if some object comes in the front, it will look like the star is in a different direction. Okay. So the way this experiment was done is that the sun, of course, comes many times in front, right? There are many stars in the sky, so often sun comes in front of some of the stars. But the problem is that we cannot collect the light, right? Because when the sun is in front of the star, we cannot see the star. So that's why this experiment was done during eclipse. Because if you have total eclipse, right, then there is no light coming from the sun. We can observe the star, and we can see at which angle the star is. We compare that with what you normally see in the night sky. Okay? And that comparison tells us that if there is a parallax, okay, that parallax is the bending of light. That parallax should be equal to this object over here. Okay, and this is what was verified in the experiment.
Sir, we will see if the star is exactly behind the sun, we will see two images of the star, right?
The point is, if the star is exactly behind the sun, right, then basically the light may not even come. Okay, that we are thinking of the light bending from two sides and coming, right?
Yes, then there.
Okay, but the point is, this angle is already big enough so that we will not see light from two ends.
But in case of very massive small object,
Yeah. So the point is, what will happen is that we will be here, light will basically go past us. Okay, the light will not reach, will not be able to collect that light. Right? So for us to be able to collect the light, the star has to be near the edge. Okay. Otherwise, the star is like going on because this bending is very small.
If it is very
Right?
large,
So it's basically like going like this. Okay, so you will not see light coming from both ends. But if there is a very massive object, okay, then it can happen. Okay, and that is what is called gravitational lensing. Okay. And typically the gravitational lensing is observed not with individual stars but with the galaxies. Right? Because if you look far, okay, there are galaxies in front of us, okay, and light from behind the galaxy, okay, can have gravitational lensing because the galaxies have a lot of mass. Right? So the amount of bending that you will see for in the presence of a galaxy, that's rho 0 is large, but still because the galaxies have a lot of mass, this ratio, okay, can be large enough so that we actually see light coming from two different sides. Okay, we will see multiple images of the object, and that is what is called gravitational lensing.
Sir, then it's from this formula to work, it has to be this condition, Gm by rho square equals mu.
That is true. Okay, it's still true. Now this is much less than 1, but it's just that it's not as less compared to the other one. And the other point is that because the galaxies are very far from us, it is possible that the line of sight, that here the problem we are too close to the sun, right? That's why we cannot see the light coming from the other two ends, right? If you are far away, we could still connect this, right? For the galaxies, we can still connect the light because galaxies are very far from us. Okay? So even if the bending is small, right, we may be able to observe it because we can actually collect light coming from both sides. Any other questions? So maybe I will not start the new subject. So next time what we will do is to focus on the massive object, motion of a massive object in this background. So it's the same equation, except that we will not set n equal to 0 anymore. And there you will see that there is a change from what we normally have in 1 over r potential in the Newtonian gravity. In the Newtonian gravity, we know that we get periodic orbits, right? Because we have calculated orbits of objects in 1 over r potential, and you get periodic orbit. Here, what will happen is that the orbit will not be periodic. Okay? All the conservation laws are still valid. Nevertheless, conservation laws by themselves do not guarantee periodicity of the orbit. Okay, at least the 9 conservation laws that you can see, the 3 conservation laws that we use to integrate the energy, angular momentum. Okay? Those are not enough to actually guarantee the orbit is periodic.
But far away.
Pardon?
For rho large, it should be.
Yes, it's still almost periodic. Right? For rho large. So if the orbit is close to the massive object, okay, then the deviation from the periodicity will be large. Okay, large in the sense it's still small, but it may be large compared to what you see from far away objects. And this is again one of the tests of general relativity. That's the precision of the perihelion of Mercury. Okay, that the Mercury orbit keeps changing.
It's almost.
Okay. It's like, so what I mean by not periodic is that it's almost an ellipse, but as it goes round and round, okay, eventually you will find that it goes round many times, but by some amount of revolution, this slowly precedes, which basically means that the orbit is not really strictly periodic, right? Because the orbit itself is changing, okay, as function of that.
But only a small part of the precession is due to gravitation.
Yes, that is true.
The rest of
Because the
most
part
of
is
it
you normally use say 1 over r potential ignoring the effect of the other planets.
Yes.
Right? So of course you have to take into account the effects of all the other planets and various other objects which are around, okay, which causes a certain amount of precision.
But that precision.
But after
is very
subtracting those, because those are explainable in standard Newtonian physics, right? But even after subtracting those, right, there is a small effect that remains, and that has to be explained by general relativity. And the reason that this effect is most pronounced for Mercury is because Mercury is the closest. Right? This precision is there for all the orbits of all the planets, but it's unobservable. It's very, very small.
So in that case, it entirely fills up the rho phi plane.
Yes, if you wait for sufficiently long, right, it will entirely fill up the rho phi plane. Meaning every point in the not entirely fill up the rho phi plane. There, of course, it's a bound orbit. Okay?
Yeah.
You cannot go very far, okay? But it basically precedes, and eventually all points within a certain radius
Yes.
will be traveled by the object once sometime.
It's a torus is.
Pardon?
The torus.
Not a torus. It's all in the plane, right? It's in the plane.
It's a phase space means this problem is after all integrable, so the
Yeah. So the phase space, of course, it's there is a standard story, right? Okay. But we'll see that the standard story doesn't help us getting a periodic orbit. Right? We have seen in the phase space also, right? I mean the periodicity of the orbit is not guaranteed. There is a torus,
Yes.
right? But periodic orbit is very special,
yes,
right? So this is in a class where that periodicity is not there. Okay? Having integrable structure doesn't guarantee that you have a periodic orbit. Yes. Right? You can have incommensurate frequency, for example. Right? The omegas can be incommensurate, in which case again they are the orbital places.
So in that case, the whole tori is filled up.
Exactly. Yeah. In the phase space, the whole tori is.
Tori is
Yeah. Okay, so I think we'll continue next time.